In this final topic area of the class, we will focus on the procedures used to test hypotheses. If you will recall from our discussion of inferential statistics, we said that the research hypothesis was a statement of the expected difference between groups or correlations between variables. The first part of this series of classes, beginning with this class, will focus on the core statistical procedures we use to determine if there are differences between groups. And the second series will focus on procedures we use to determine if there are correlations between variables. The primary way we detect differences between groups is to determine if the means are different, or what we will come to call significantly different. Thus, if we have a clinical study of depressed adults, we might hypothesize that the group receiving an experimental psychotherapy will be less depressed at the end of treatment than the no treatment control group. If we are measuring the construct depression using the operational definition of scores on the Beck Depression Inventory, then we would expect the treated group to have a lower mean score than the control group. This would be our research hypothesis. Our null hypothesis would be that there is no difference between the mean scores of the two groups in the population. Thus, our statistical procedures will have to be able to detect differences between mean scores. The primary statistical procedures we use for this type of problem is the t-test and the f-test, and the f-test is also called analysis of variance, or ANOVA. Technically, the z-test can be used to test means. However, in practice, this is generally not the case, because if you remember, the z formula uses the variance of the population, which in actual practice we rarely know. The t and the f replace the z when we use the sample variance to estimate the population variance. But probably the best way to learn about the t and f test is by first learning how we might use the z-test to evaluate hypotheses concerning means. Let's try to do this by modifying the example experiment I mentioned in our last slide. Let's say we knew that the mean and the standard deviation of the Beck Depression Inventory in the population of depressed adults. For argument's sake, let's assume that the distribution of BDI scores in the population is normal, and the mean of the test is 17, with the standard deviation of the test equal to 10. Now let's say we select a sample of 25 depressed adults from the population. We administer the experimental treatment, and at the end of treatment we find that the mean score for this group of adults is 12. Our research hypothesis would be that the treated group would have a lower mean score than the population. And the null hypothesis would be that the mean of the sample would be 17, or would be equal to, or that the sample mean would be equal to the mean of the population. Before going to the next slide, apply the z formula we have learned to this point for the data we have just described. What z-score would we wind up with, and what would be the probability of receiving a score of 12 or lower? Applying the z formula we have learned up until now, we would wind up with a z equal to negative 0.5. We would subtract 17 from 12 and divide by 10, which would lead to an answer of negative 0.5. From the z-table, we would learn that the area under the normal curve that falls below a z equal to negative 0.5 is 0.3085. We know from our earlier class on inferential statistics, we reject the null hypothesis when the test statistic exceeds a critical value. And we know that when alpha is equal to 0.05, that when we're doing a two-tailed test, the critical value of the z distribution is plus or minus 1.96. Thus, the test statistic of negative 0.5 does not exceed the critical value, falls instead in the region of acceptance, and we would not reject the null hypothesis. In addition, the probability associated with the area below the test statistic is 0.3085, which is not less than 0.05. However, if we left it there, we would have made a serious error. Note that the formula for the z that we have used, that we have learned, is x minus mu, where x is an individual score, a single score. But in this example, we have a mean of 25 participants, or essentially 25 individual scores brought together into one summary statistic. So our formula needs to change in order to deal with group phenomenon instead of individual scores. The big reason we need to do that is that the variance in the population of 10 is the average distance a single score can be expected to fall from the population mean. Rather, what we need to know is the average distance a group score or a sample mean will fall from the population mean. By turning to the next class, we will learn that the standard deviation for a sample mean is much smaller than for a single individual score.